surprised everybody responded immediately. So I think there's maybe one or two people that I know of that haven't responded yet. So if you're one of the people that haven't responded, please do that.
How many do you have? How many do you got?
There's about 20 people that responded.
That's the minimum that we need.
Yeah, we've got enough people, but they asked for they wanted the addresses of the people that were in the club. So it'd be a good idea if we did that.
How many non-residents you got?
Oh, I've got about 20 other. There's about 40 40 total. But some of them I think are not really following us. So
Right, Bruce.
So I'll prune that down after this go around.
Who's paying for the room? Should we divide it up?
Oh, we'll talk about that later. I think that's not a problem. It's a very small amount.
Also, we have to discuss next week because that's Thanksgiving week, and I'm sure people are going to be away. Some, anyway. Are we going to hold a meeting then? I may not be here.
Let's take a vote. How many would prefer turkey to physics?
It's kind of unfair of it. Not coming, or won't be here?
Yeah, let me put it the other way. How many would like to come next week? Yeah,
I think we have 4.
I think we have a quorum, yeah.
if Ernest we have another topic area, which is how things work.
Okay.
I hate to give you, it's only going to be 4 people here.
I may be here, I'm not sure. The plans
Yeah,
are-
but the rest of us won't be able to hear Ernest talk. It sounds interesting. I'd love to hear
Well, he's going to give more. He's got a whole list of how things work, and you.
I can give a dry run next week, and then you guys can consider if it's worthwhile.
it. Oh, okay.
Would you prefer to have a week off?
Yeah, I may not be here next week.
Yeah,
I don't know for sure, but I may not be.
We will next week. We'll have Ernest talk about what you're going to talk about transistors, how transistors work. Is that right?
Yeah.
So we'll schedule Ernest for next week and
I'll be here next week, but I won't be able to talk because I'll be in Joshua Tree, so don't have good Wi-Fi connection.
Don't cut down any of the trees, Bob.
Send me a little thing that I can send out.
Joshua Tree is interesting. You can hike there.
I know, I've been, yeah.
Oh, you've been there?
Yeah. It's a neat park. Bob, let me take 10, at most 15 minutes to
Go for it.
that's where we are, and then we'll put you on. So I'm going to need the screen.
All right, I'll set you up as host.
Okay.
All right, you're now host.
Well, I see you. I don't see my screen. I see, how do I get my screen?
You're the host, so you should just be able to go to your zoom.us, command tab to zoom.us, and you should be there.
He said command, you have to hit the command key. Command tab, he said.
I'm sorry.
Command tab to zoom.us.
Okay. Let's see.
I can see you fine.
Okay, you're there, Steve. Oh, yeah.
Yeah, so I'm just gonna show a couple of slides and summarize where we are, and then Bob is going to.
Yeah, share your keynote so that I can see it.
I'm impressed with how easily Steve could get up and
Got a little green share. There you go. Great.
relocate.
Okay, there's a bit of a share screen thing on the top, but well,
Yeah, don't worry
So be-
about that. This
be
is exactly what I was looking for.
okay. Well, one of the things that we looked at last time was the feature of quantum mechanics. We looked at several features of quantum mechanics that distinguish it from classical mechanics. One of them was the phenomenon of entanglement. And we looked at the Einstein, Podolsky, and Rosen argument, which basically set locality against quantum mechanics, against the some of the predictions of quantum mechanics, arguing that quantum mechanics was incomplete or not right. Something was missing in quantum mechanics. And then to address this question, again, we were left with two choices, locality versus quantum mechanics, with quantum mechanics was suggesting some non-locality aspects. Now, locality, I just have to emphasize, was extremely important concept to Einstein, as it was to many other physicists. If you think about it, if things are non-local, you could argue that maybe it's impossible to do science. Why? Because to do science, you typically have to isolate the phenomenon you're interested in investigating, so you can do controlled experiments. But if your experiment will result depends on what's going on in Alice Missouri, you've got stuff you can't control. So again, locality was a very, very difficult concept to give up. Now it turns out, according to the result of the experiments following Bell's publication of his inequality, that indeed, of the two choices, you've got to give up locality. Turns out, though, that it seems anyway, that the non-locality phenomena is subtle enough that it doesn't seem to be impeding the progress of science. It's there, but it's very subtle. The other aspect of quantum mechanics we talked about was the phenomena of superposition, that it seemingly suggests that a particle, for example, could be many places at the same time, and only when you look or do an experiment to ascertain its position does this superposition seem to disappear and the particle appears at some specific location. For example, if you set up a double slit experiment and shoot one particle at a time and don't try and determine which slit the particle goes through, the wave function describing the quantum mechanical system suggests that the particle goes through both slits, or something is aware of both slits. The traditional interpretation, or I should say the traditional story the story that one picks up when one studies quantum mechanics in a graduate course, for example, is that the wave function describing the particle does indeed go through two slits. However, when you try and determine where the particle is, say by setting up a photosensitive screen behind the two slits, the particle is going to appear at one particular location. This is sometimes referred to as the measurement problem, namely that making a measurement seems to fundamentally alter the system you are measuring. That's what it seems.
No, that's how you interpret it by trying to understand it in classical terms.
I understand. And that's what I said. That's what it seems. I'm going to relinquish the microphone in just a minute. Let me finish this with an experiment you've all probably heard at one time or another, the famous Schrödinger cat, so-called paradox. You have a cat that's in a box, and in the box there's a device which is triggered by the decay of a radioactive element. When that radioactive element decays, it sends a signal to a device which releases a hammer, which breaks a vial of poison, and the cat dies. So let's suppose you wait 1 half-life of that particle that is radioactive. Okay. Then the superposition that quantum mechanics tells you must be there is a live cat and the particle not having decayed, and a dead cat and the particle having decayed. So this seems like something nobody's ever observed. You never observe a superposition of a live cat and a dead cat in a box. Well, the story went that if Schrödinger walked into his lab and opened the lid of the box, one of those two alternatives would become real and the other would disappear. Which one? Purely a subject of probability. Equally dead cat, equally live cat. The mathematics is simple. You have a superposition, a state which represents a superposition of two states, live cat and dead cat. The measurement alters the, again, I'm talking traditional quantum mechanics, the kind of quantum mechanics that has been traditionally taught in universities. The measurement process alters this superposition, this wave function. As a result of the measurement, this or this results. Okay. And again, traditionally, this has been described as the collapse of the wave function. The wave function, which heretofore represented a superposition of two possible states, upon making a measurement, only one of the two possible, or many possible states, depending on what the system is you're investigating. But the measurement results in one result, and the wave function is transformed irreversibly by that procedure of making a measurement. So again, one outcome of this kind of methodology or philosophy, you might say, which is referred to as the Copenhagen interpretation, and for 30 years was the prevailing story about the measurement problem in quantum mechanics. David Mermin, who is one of a number of people who are arguing against this interpretation, suggests the following. If we were to sum up in one sentence, what the Copenhagen interpretation says to me, it would be shut up and calculate. In other words, just don't think about it. The last slide I want to show before I hand over the gavel to Bob is the traditional, again, this is the Copenhagen view of what the basic rules of quantum mechanics are. Rule 1, given the quantum state of an isolated system at one instant, there is a law that will predict the precise quantum state of that system at any future time. In non-relativistic quantum mechanics, that's the Schrodinger equation. I don't think very many people argue with that rule. The second rule, however, is the one that's controversial. The second rule says the outcome of a measurement can only be predicted probabilistically, but afterward, the measurement changes the quantum state of the system being measured by putting it in the state corresponding to the result of the measurement. This is sometimes referred to as the collapse of the wave function. So here, with the second rule, it's impossible to really separate the observer from the observed. And the folks that adhere to both of those rules are frequently referred to as instrumentalists, in the sense that they say all quantum mechanics can do is to tell you what you're going to measure with what probability if you make a measurement. But it won't tell you anything about what lays behind that reality, because the reality itself is so amorphous, depending on what kind of a measurement or what kind of an interaction occurs between the observer and the observed, that it's impossible to envision some sort of reality independent of the observer. So the people who want to provide some kind of reality that lies behind quantum mechanics, something that doesn't depend on the observer, have to abandon rule 2 and either just stick with rule 1, which we'll see later is the idea behind the many worlds interpretation of quantum mechanics, or add something to rule 1, which is what the pilot wave theory that Bob is going to describe in a second does. So we have these two schools of thought about what, how to view quantum mechanics. One involves those two rules, the other, the realist, wants to develop some idea of an underlying reality behind the kind of interactions you and I perform every day with things. We don't want them to somehow rather morph reality in an uncontrollable way. So Bob, I'm going to hand...
yeah, you got to make me host again.
Yeah, okay. Can you make yourself host, or do I have to do it?
You have to do it.
What do I do?
Go to the participants and then you'll see you've got the, okay. I think, no. Reclaim host. Let me try it. Okay, looks like I have host.
Good.
Okay, great. Let me now share my screen. And hopefully everybody can see the keynote. Is that true?
Yeah, but it's not full screen yet.
Let's see. I got it set as full screen here. I mean, it only takes up 3/4 of it, but that's just the way the keynote works. I think that's as much as we're going to do.
Okay.
Just hit on your green dot, that might blow your screen up. Upper left corner green dot of the window you're in. Just click on the green dot in the upper left corner of your screen. There you
I
go.
can't understand the things being said.
There we go. It's full screen now.
Okay, great. All right, so I'm going to be talking mostly about John Stewart Bell and David Bohm. And David Bohm sort of reinvented what de Broglie had done in 1927. And a lot of work has been done beyond what was done in 1927 by de Broglie. Many people at the time sort of dumped on de Broglie, especially Pauli, who was quite critical. He's the one who made up the quote, "not even wrong," when talking about various things in quantum mechanics. Anyway, it was not well understood until the 1950s when John Stewart Bell looked into it. And it was because von Neumann had wrote a proof, quote unquote, that you couldn't you could not get a version of quantum mechanics that would have what were called hidden variables. Of course, hidden variables is by itself a word that hidden has some kind of mythical approach to it, but in point of fact, all we're doing is talking about positions, and positions are the only things that you ever get in an experiment. Even if it is a meter showing an arrow someplace, it's the position of the arrow that tells you the result. So positions are everything. Anyway, we'll move on. In the 1850s, Maxwell said, the first processes, therefore, in the effectual studies of the sciences must be ones of simplification and reduction of the results of previous investigations to, yeah, okay, sorry. I've got a screen up here. Can you see, are you seeing it?
Yeah.
The gift of Zoom?
Yeah, we got it. We're okay.
I don't know how to get rid of it. Let me get out of here.
No, you're fine. Oh, you're fine here.
Okay, well, I couldn't, it was in the middle of my screen, unfortunately. All right, so this is the Irish physicist John Bell. And he worked at CERN, designing various kinds of instruments there. And he talked about himself as a quantum engineer. But he gave a series of informal lectures at CERN on Sundays. And on Sundays, I have principles. So he was very, very upset with the Copenhagen interpretation. Conventional formulations of quantum theory, and of quantum field theory in particular, are unprofessionally vague, ambiguous. Professional theoretical physicists ought to be able to do better, and Bohm has shown us a way. So, supposedly, quantum mechanics is about measurements, but who does the measuring? What is a measuring device? Is the measuring device also a part of the quantum system? And what is the role of language? These are all important questions which the Copenhagen interpretation pretty much ignores. So it would seem that the theory, quantum mechanics, is exclusively concerned about the results of measurement and has nothing to say about anything else. What exactly qualifies some physical system to play the role of measurer? Was the wave function of the world waiting to jump for thousands or millions of years into a single-celled living creature appeared? Or did it have to wait a little longer for someone better qualified system, maybe with a PhD? If the theory is to apply to anything but highly idealized laboratory operations, are we not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere? Do we not have jumping then all the time? I mean, one of the things that was very good about Bell was he would ask extreme questions, which the Copenhagen experiment the interpretation just ignored. The first charge against measurement in the fundamental axioms of quantum mechanics is that it anchors the shifty split of the world into system and apparatus. In the Copenhagen experiment interpretation, it is an axiom that the apparatus has to be classical. It has to be a completely classical system. Whereas the quantum system is not. And they cannot describe how you split between the quantum system and the classical system. That's the shifty split that he's talking about. A second charge is that the word comes loaded with meaning from everyday life, meaning which is entirely inappropriate in the quantum context. When it is said that something is measured, it is difficult not to think of the result as referring to some pre-existing property of the object in question. This is to disregard Bohr's insistence that quantum phenomena, the apparatus, as well as the system, is essentially involved. So he's talking about here how in the Copenhagen system says it must have a measuring apparatus, That measuring apparatus has to be classical and has to be completely separate from the quantum system. And this makes no sense. If it's going to be a quantum system, it should be a quantum system because every classical system is made up of atoms, and all of those are quantum mechanical. If it were not so, how could we understand, for example, that the measurement of a component of angular momentum in an arbitrarily chosen direction yields one of a discrete set of values? When one forgets the role of the apparatus, as the word measurement makes all too likely, one despairs of ordinary logic, and hence quantum logic. When one remembers the role of the apparatus, ordinary logic is just fine. We'll talk about it in a little later, but the Cocken-Specker's theorem basically says that all quantum systems are contextual. The results of an experiment depend upon the way you set up the experiment, the context that you set for the measurement. And this is, if you carefully follow that through, you find that ordinary logic works just fine. In other contexts, physicists have been able to take words from ordinary language and use them as technical terms with no great harm done. Take, for example, the strangeness, charm, and beauty of elementary particle physicists. No one is taken in by this baby talk. It would be so with measurement. But in fact, the word has such a damaging effect on the discussion that I think it should be banned altogether in quantum mechanics. This was a picture that was done by Bertelsmann. He had always worn socks with two different pairs, and Bell looked at that and said, if you know that one of them is pink, you know the other is not pink. And that is very analogous to what's going on in entanglement. Anyway, quote, hidden variables. In 1952, I saw the impossible done. 1952 was when David Bohm wrote about Bohmian mechanics, and the impossible he's talking about is von Neumann's impossibility theorem that says you can't find a hidden variables theorem, a hidden variables version of quantum mechanics. We'll talk a little bit about hidden variables and von Neumann's no hidden variables proof. Bell quite clearly understood what was wrong with von Neumann's argument. Von Neumann had illegitimately extended his putative hidden variables as a result of the variables of quantum theory, that the expectation value of A plus B is equal to the sum of the expectation values of A and B. And that is certainly true for commutative operators. But for non-commutative operators like position and momentum, that is there's no reason to believe that that would be true. Once this mistake was realized, it was clear that hidden variable theories of quantum theory were totally possible.
Bob, have you explained the word commutative?
Okay, commutative. If you have 3 times 4 equal to 12, it's equal to 4 times 3. But for many kinds of mathematical quantities, usually called operators, you can have A times B is not equal to B times A. And the uncertainty principle basically says that any operators that are used for measurements do not commute, that is A times B minus B times A is equal to something, not 0, then those will have a relationship, a duality between them that forces them not to be able to be measured simultaneously. David Bohm, shown here on the left, said many things, but one I like in particular. A great many people think they are thinking when they are merely rearranging their prejudices. In his version of quantum mechanics, he accepts the wave function from Schrodinger equation, but he has 3 processes. The first is just a rearrangement of the wave function. So you can rewrite, the wave function is a complex number, a plus ib. You can always turn it into a real number. Here, r of x and t is a real number, times an exponent of an imaginary number times a phase. And the phase here is s of x and t. So you rewrite it so that there's a real part and the imaginary part is all in the phase, s. Then he has a continuity equation for the probability distributions. And the last thing is the Hamilton-Jacobi equation, which gives the phase as a function of the phase and the real part. So this looks very much like ordinary classical mechanics. Hamilton-Jacobi is classical mechanics. But there's this additional term on the end, h bar squared, the Laplacian of the real part divided by 2 times the mass and the real part. That is what is called the quantum potential. And it is the effect on the quantum potential that creates all of the interesting results in quantum mechanics.
Bob,
Yeah?
how can A times B minus B times A be anything but 0?
Because you can write many kinds of objects other than numbers. And in particular, we can write matrices. That is, I've shown a few times where you have, for instance, the metric of space-time is a 4x4 matrix. And the gravitational field is a 4x4 set of numbers at every location in space-time. Now, for the ones usually done in general relativity, they are commutative, but you can write matrices that are not commutative. So, and it is in particular those kinds of matrices that give you results like position times momentum, as those are not commutative operators in
Well,
quantum.
it's also true that of the three-dimensional, 3 by 3 matrices in ordinary geometry, you can't commute the 3 by 3 rotation matrices. That if you change the order, you get a different matrix.
Yeah, no, I'm just saying there are a lot of things that can be created that have many different values, and A times B is not necessarily going to be equal to B times A.
Rotate a book about the horizontal axis and then about the vertical axis and reverse that. Rotate about the vertical axis, now about the horizontal axis, and you get a different book. Yeah.
Some of the
Put your
confusion here
socks
arises.
on in a different order, and you'll come out with a different.
Some confusion arises because the word multiplication is used. It happens that this operation of matrices obeys all the laws of multiplication, except the commutative one. So it's, the word multiplication is used, and then people feel that ordinary number multiplication, they know what that means. That should apply also to these cases. But in the case of matrices, the commutative rule is not valid. But
Yeah.
the word multiplication is still used.
If you've got a book there, you can do the rotations in 2 different orders, and you'll get different results.
Yeah, we just did that.
You just did.
All right, good. All right.
What about stocks?
Oh, the operator of putting your socks on and your shoes on don't commute. If you put your socks on first, then your shoes, you get one result. You do it the other way,
Doesn't work so.
it looks very different.
Okay, so what are the basic postulates of Bohmian quantum mechanics? First is that a physical system consists of a spatiotemporal propagating wave, that's the actual Schrodinger wave, and a point particle is guided by it. So the particle interacts with the wave and follows a direction depending upon the wave. So the wave is described mathematically by the solution of the Schrodinger wave equation. The particle's motion is described simply by the derivative, the velocity of the time is the gradient of the phase in the wave function. So you integrate that and you get the particular positions. It is, of course, dependent on the initial conditions of the of each particle to begin with. And one of the problems is that we don't know the initial conditions of the particles. So we often have to use a initial description of the wave function, which gives many, many different possible results. And if you're doing the particles one at a time, only one of those is actually going to be observed. So they're often called empty waves. Okay, so the probability, the last one is that the probability density, rho, to find a particle in a differential volume dx cubed is exactly equal to psi squared, that is the Born equation. So this is a picture of what happens with the particles. We have a whole bunch of particle possibilities here at the bottom. If you are doing them one at a time, one of them goes through, but you don't know which. And let's see. You can see that they start spreading out and moving around, and the particles all observe in bunches around where the wave portion of the result that you would see by having a screen there show up. So these are literally the locations of every possible one as it goes through. It starts out in the classical form, but quickly goes back to the interference picture that you see normally. So this is the way in which the collection of results should be. This is a detailed explanation. You'll notice that any particle that goes in through the top slit will always be on the upper half of halfway above the slits. Any ones that come below stay below that. Now, this is the same kind of picture done by photons in Bohmian trajectories, and they're similar but slightly different. Now, this is actually an experimental result. If you take what are called weak measurements, which were done by Aramov and David Albert, and I can't remember who the third guy was who did them. The idea is that you take momentum, in this case, the circular and the horizontal and vertical polarization. If you take them not by strong measurements, but by very weak measurements, that is, you have you don't have a strong polarizer connection there to know exactly what the polarization is. You take it very weak, then you can measure the position, and you can have them both be less than the uncertainty position. Now you do it again and again and again and again, and because of the results of statistics, you can make the positions arbitrarily close, because you just do it enough times and it goes down 1 over the square root of the number of measurements, and you can make them as close as you want. As you can see, the results of the physical experiment are somewhat similar to the computed results in the two. The other way of doing the Bohmian results is called the hydrodynamic version of quantum mechanics. And this is where a system is set up where there's a bouncing oil drop on another vibrating surface of an oil pan. And you can take a look and you'll see that there's many interference effects when you look at it. And of course, when it's dropping around, it's creating small droplets, and it can be moved around. This is on the left, lower left is just not a real spring, but showing the results of what it would be like if there were connection between a spring, and you get the position, and you can get the particles going around in a circle. All of these things can be computed quantum mechanically. And on the left here, you have some collection of the various particle. If you're doing the center one here shows the two slit, and you can see the positions move along the surface of the film when it goes through. And you get all kinds of quantum chaos going through all of these various pictures. This is for a circular disk, and the top shows the actual collection of particles that drops were going around in it, and it just gets very, very confused. But when you take and look at the section marked B, those are the probabilities associated with every position in this object. And on the right is what the quantum mechanical computing results are. They are, again, similar, not exactly identical, but very, very, very similar to the kinds of results you get from quantum mechanics. So let's talk a little about Einstein versus Bohr, and I'm clearly
Can I stop you a little bit to digest what you just said?
Sure.
Are you kind of telling me that if I had a drum and I hit the top of the drum and I put a small particle on top of the drum, that the vibration of the drum would move the particle about?
Well, it would, but in this particular case, you're dealing with two liquids. And because they're liquids, they create waves, and the waves interact with each other. If they were on a surface of a drum, you would not get the same results that you get on the surface of a hydrodynamic surface. But yes, you would get particles bouncing around on a drum, but you wouldn't get these results.
Okay.
Is that clear?
Yeah, you're saying these are closer to the quantum mechanical results. But
Yes, and that's because they're dealing with the film of oil, which is a liquid and does have all of Huygens principles, so that you get interactions between them. And the oil drop creates more. They interact with each other. It moves around, does all of the things that you would expect. Is that clear?
yeah, so you're saying that the system of equations that you get with the oil film is the same as you would get is an analog to what you'd get in quantum mechanics.
Exactly.
That they're the same equations in both cases.
Yes.
Okay.
That's what's called the hydrodynamic version of quantum mechanics. And there is even beyond that a completely classical set of equations that you can run that will reproduce quantum mechanics. So everything that Einstein wanted to show to be true can be shown to be true. So once again, Bohr was completely wrong.
Now, were you plotting psi star psi there?
Yeah, these were psi star psi on the left and right.
Oh, okay.
So let's take a look at a few things on Bohr and Einstein. Bell, I thought, said it very well. I feel Einstein's intellectual superiority over Bohr in this instance was enormous. A vast gulf between the man who saw clearly what was needed versus the obscurantist that Bohr was. Mary Gell-Mann said it even better. Niels Bohr's brainwashed a whole generation of theorists into thinking that the job of interpreting quantum mechanics was done 50 years ago. And again, Bell said everything has definite properties. David Deutsch said the mid-20th century Bohr-Einstein debate about quantum mechanics is often misinterpreted as a personal clash between wizards. So counterintuitive are quantum theory's predictions that under the leadership of one of its pioneers, Niels Bohr, a myth grew that there's no underlying reality that explains them. Particles get from A to B without passing through the intervening space where they have insufficient energy to exist. They briefly borrow the energy because they are uncertain about what their energy is. Information gets from A to B without anything passing in between, what Einstein called spooky action at a distance, and so on. So while most accounts say Bohr won the debate, my view is that Einstein, as usual, was seeking an explanation of reality while his rivals were advocating nonsense. Schrödinger, Bohr's standpoint that a space-time description is impossible, I reject limine. Anybody a lawyer in here? I guess not. Limine is a legal term, and it means that these are objections that are done outside the audience of the jury. That is, their arguments done in the judge's offices, not in the court. Physics does not consist of atomic research. Science does not consist only of physics, and life does not consist only of science. The aim of atomic research is to fit our empirical knowledge concerning it into other thinking, our other thinking. All of this other thinking, so far as it concerns the outer world, is active in space and time. If it cannot be fitted into space and time, then it fails in its whole aim, and one does not know what purpose it really serves. Just to encourage what Schrödinger said, many of the ideas were that, when quantum tunneling occurs, you run up against a a wall that's too high to go through and suddenly you find it on the other side. Well, according to the Copenhagen interpretation, that takes no time. That has clearly, just within the past year, experiments have been done to show that they take a finite amount of time. And furthermore, you can start them going through and you can actually turn them around and go back. So all of the stuff that that Bohr said is just nonsense. Their dispute went to the fundamental heart of the design of the cosmos. What was there an objective reality that existed, whether or not we could ever observe it? Are these laws that restored strict causality to phenomenon that seemed inherently random? Was everything in the universe predetermined? This was just his interpretation of what was going on. E.T. Janes, who basically single-handedly got physics into Bayesian probability, said Einstein's thinking is always on the ontological level traditional in physics, trying to describe the realities of nature. Bohr's thinking is always on the epistemological level, describing not reality, but our information about reality. Leonard Susskind, another person that I respect, both Bohr and Einstein were subtle men. Einstein tried very hard to show that quantum mechanics was inconsistent. Bohr, however, was always able to counter his arguments. But in his final attack, Einstein pointed to something so deep, so counterintuitive, so troubling, and yet so exciting that at the beginning of the 21st century, it has returned to fascinate theoretical physicists. Bohr's only answer to Einstein's last great discovery, this is the EPR argument, the discovery of entanglement, was to ignore it. To this day, many researchers agree with Bohr's pragmatic attitude. The history books say that Bohr has proved Einstein wrong, but others, including myself, suspect that in the long run, the Einstein view might return and that there is something missing in the Copenhagen interpretation. Einstein's original objections could be overturned, but problems still arise if one tries to formulate the quantum mechanics of the entire universe, where measurements can never be repeated. And if one tries to reconcile the laws of quantum mechanics with the throes of gravitation. This is the Nobel Prize winner, Gerard 't Hooft. Bohr's version of quantum mechanics was deeply flawed, but not for the reason Einstein thought. The Copenhagen interpretation describes what happens when an observer makes a measurement. But the observer and the act of measurement are themselves treated classically. This is surely wrong. Physicists and their apparatus must be governed by the same quantum mechanical rules that govern everything else in the universe. Steven Weinberg, another Nobel Prize winner. Nobody knows how the stand of our knowledge about the atom would be without him. Personally, Bohr is one of the amiable colleagues I have met. He utters his opinions like one perpetually groping and never like one who believes himself to be in full possession of the truth. This was Einstein's friend Bohr. Bohr and Einstein were friends and had great respect for one another, but they were also stubborn. It is wrong to think of the task of physics to find out how nature is, said Bohr, and Einstein disagreed. What we call science, Bohr said, has the sole purpose of determining what is. Very well. On non-locality. Non-locality disturbed John Bell deeply, since for him it was equivalent to the breaking of the Lorentz invariance, a feature he could hardly accept. He often remarked, "It's a great puzzle to me. Behind the scenes, something is going faster than the speed of light." This was a cartoon that Bertelsmann drew for John Bell's, I think, 60th birthday, if I remember correctly. I am saying that this theory displays the utter irrationality, that somewhere in the theory is lost the distinction between the reality and the knowledge about this reality. The result have traits more of medieval black magic than of science. Julian Jaynes is another great Bayesian probabilitist, whatever. Anyway, I hesitated to think it might be wrong, but I knew that it was rotten. This is John Bell talking about quantum mechanics. He didn't think it might be wrong because it had so many good results, but there was something rotten in the middle of it. These are the people we've been talking about: Susskind, Bell, not Jaynes. Yeah, Jaynes, Bohr, Gelman, Einstein, Bohm, 't Hooft, Schrödinger, Albert, Weinberg, Goldstein. He's a prominent physicist from Rutgers who is very prominent in the Bohmian community. Tim Maudlin, who's a philosopher who is very good physicist as well. Wojciech Zurek on the bottom left is the one who has pretty much created almost all of decoherence, and this will be a very important result later in the book. So I'm just showing his picture. And then, of course, there's Einstein and Bohr, Bertelsmann, and all of the people's names. So, hidden variables works, a Newtonian slow velocity version of the particle position, the particle motion in quantum mechanics can be described. The Bohr probabilities are reproduced in the trajectories. A particle photon trajectory can be computed. Experimental measurements are very similar. And the hydrodynamic version of quantum mechanics experimentally produces the results of quantum mechanics, whether it's the two-slit experiment, the quantum chaos, all of those things have been done and shown the same kinds of results as you get from quantum mechanics. So Bell actually was a beginner on decoherence. The idea that the elimination of coherence in one way or another implies the replacement of and by or is a very common and one among solvers of the measurement problem, and it has always puzzled me. The and and or is the superposition stuff. The superposition is not something special. It just says that the solution of the Schrodinger equation is linear. You can take any solution of the Schrodinger equation, any number of them, an arbitrary number, and any linear combination of those is also a solution of the Schrodinger equation. And that's all that superposition means. That you can take they're linear in the solution, and that's what's called superposition. So Bell anticipated the great insight into quantum mechanics in the last couple of decades, namely decoherence, which is another topic we're going to discuss in quite a bit of quite a bit of time. So at some point, I will go back and show a Lagrangian which reproduces the quantum mechanical trajectories without the Schrodinger equation. Any questions?
I'd like to ask one. Where does this put time, both classically and in quantum mechanics?
Sorry, can you repeat that again closer to the mic? I can't understand what it's.
I'm sitting way in the back here. I'm interested in what this means about time in the quantum world and also in the classical world.
Sorry, would somebody repeat the question to me close to the microphone?
Yeah, I'll repeat it. What does this mean about time in both the quantum world and the classical world?
I'm sorry, please, I say it slower.
Okay, I'll ask. What does this mean about time in both the quantum world and the classical world?
Well, remember, this is the Schrodinger equation is a slow velocity. It's a Newtonian type of result, not the results of special relativity or general relativity. And similarly to that, the time is essentially like Newtonian. There's a time and there's a space and they're separate, and they go on as classical results do. Now, there have been many people working for the last 25 years or so who have shown how to make Bohmian quantum mechanics relativistic. It is a very hard problem to solve, but it's very similar to the kind of work that Dirac did in making everything a field. And when you do that, then of course you get all special relativity as you do in quantum field theory. But that's not the original Bohmian version. The Bohmian version is purely Newtonian. That is, space and time are separate and time goes forward. It is only when you go to field theory you get special relativity. And that's true in quantum mechanics as well. Quantum mechanics will not use Lorentz invariance. It is only quantum field theory that is Lorentz invariant.
Bob, do you know how the pilot wave theory deals with spin?
Yeah, there is a way to do it. It requires having, just like Dirac did with, he had a 4-component spinor. You need a higher complex version than the particle version that I've been discussing here today, but you can deal with it.
Just a comment, I think the pilot wave theory, one of its importance is that it's a counterexample of von Neumann's theorem, which of course is proved wrong. But there's some prices you have to pay. One, of course, is that the pilot wave theory is highly non-local.
Yeah, but that's a function of it's very similar to Newtonian gravitation, which was also completely
True.
non-local. It is until you get to field theory that you can incorporate special relativity. And that's true of all kinds of quantum mechanics. Quantum mechanics just simply is not Lorentz invariant.
Now, has the attempt to make pilot wave theory Lorentz invariant, has that actually been done, or is that a work in progress?
Well, they have done, they are able to reproduce the electron in Dirac's version. It's not clear to me that they've been able to do anything on the quark fields or many of the other fields. The only one that I'm fully aware of as being is for the electron, similar to the Dirac equation. Now, I am not an expert on this, so I could be wrong, but that's my current understanding, is that the only one that is fully relativistic is the electron, similar to the Dirac equation.
Another comment, one thing that was intellectually pleasing, despite all its nonsense, of the wave function collapse, the so-called Bohr interpretation, is that anytime a measurement was made, the wave function collapses to one of the eigenvalues of the measurement, one of the possible results of the measurement. It's like taking a dusty house and sweeping it clean, then you start fresh. With pilot wave theory, anytime you're presented with a choice, the possible superposition, of course, the particle follows one of the waves. The
other one's empty.
I'm sorry?
The other one is what is called empty, because you don't know which of the initial conditions create the two situations.
But you have a double slit.
One of them occurs in the initial conditions. So
I understand all that. You have a double slit experiment, and the particle goes through one slit. Of course, the wave goes through both slits and interferes behind it. But that continues forever. So every time you perform a double slit experiment, or any experiment which involves a superposition, you adding to the propagating pilot waves that have been created forever. So the universe is awash with pilot waves, empty pilot waves. And I think this is, again, the intellectual baggage that is associated with a pilot wave theory.
Well, there is a as I said, I will show a Lagrangian, which produces quantum mechanics trajectories without the Schrodinger equation. Purely Hamilton-Jacobi. And it can be done. So, and again, the whole problem is you don't know the initial conditions. If you knew if you could measure the initial conditions, you could know the exact particle trajectory. The only emptiness in it is the fact that you don't know the initial conditions. That those empty waves are simply the fact that you don't know the initial conditions. If you knew the initial conditions precisely, you would not need the empty waves.
We'll be interested to see this.
Yep. Any other questions?
Yes, why can't you set, experimentally, why can't you set the initial conditions?
Steve, could you repeat that for me, please?
Yeah, the question is experimentally, why can't you set the initial conditions? In other words, why can't you precisely set up an experiment so that the initial conditions of a particle, for example, are completely determined?
Because the only way you can measure things with precision is weak measurements, where you only partially measure, a small portion of the momentum and a small portion of the position, and you do them over and over and over again in order to be able to get the trajectories. But if you do a partial measurement like that, a weak measurement of the initial conditions, you'll get a whole collection of results, the same way you do from the normal way of setting up the wave function.
Well, you've got a particle and you've got a wave. Is there a simple physical picture of why you can't make precise measurements on either of those so that you can ascertain both the position and the momentum?
No, any linear system like the Schrodinger equation means that there's two dual representations of that, either the momentum or the position. And those two, just when you do ordinary electrical engineering on frequency and time, you can't measure them simultaneously.
Yeah,
Linear systems.
That's
the same thing is true of Schrodinger equation. And if you measure the position with sufficient accuracy to get the position of the initial conditions, you'll disturb the momentum.
No, I understand.
That's the usual. That's what. You didn't break quantum mechanics. The fact that they're linearly solutions of Schrodinger's equation means there's no way to measure position and momentum simultaneously.
No, I understand that. But you're giving us a picture of a wave and a particle. Okay. Now the question is, suppose you measure the wavelength of the wave precisely. So that gives you a definite state of momentum. And then you go and measure the exact position of the particle. You've got a particle there. You measure the exact position of the particle. Now, why can't you do that?
Because you need both.
I know. You measure the wave, and then you go and measure the particle. Now, in measuring the particle,
but you're moving, when you're doing the second measurement, you can't do them simultaneously.
So the picture of a wave and a particle is a little bit more complicated than just saying that the two are sitting there separate. And presumably, if you've got a wave and you've got a particle and there's two separate entities, you can make a measurement on one without disturbing the other. And apparently, that's not the case.
Right. The closest you can come would be trying to get the position of the bouncing oil drop on a oil pan. And every time it's bouncing up and down so that it's moving in the pan of oil, and you have this, all of the solutions are linear and you can't measure them simultaneously. I mean, that's true in electrical engineering. It's true in quantum mechanics. It's true in the hydrodynamic version of quantum mechanics. You just, that's the nature of anything that is linearly additive.
All right, and you're still talking about a pilot wave and a particle as if they're two separate entities.
Could you repeat the questions for me, Steve?
Yeah, the question was, you're still talking about a pilot wave and a particle as two separate entities.
Well, you need, in the Bohmian version, the wave function is something that is ontologically real. It is a field that is everywhere. And your particles are moving through that field.
Is that wave function what we would consider psi in classical quantum mechanics? Is that
Steve?
Is the wave function, what was your question?
psi star?
Is that's basically psi star psi. But the wave function is the Schrodinger equation psi for psi.
Yes, it's exactly the same solution as any quantum mechanical solution that you would get in quantum mechanics, you get in Bohmian mechanics.
Bob, I have this question about the Bohmian formulation. If you say the particle arrives here because it was determined to have arrived there by initial conditions and not somewhere else, for example, the particle arrived somewhere else because its initial conditions were different. Can you reverse engineer the math and calculate what the initial conditions were?
Steve?
Can you repeat that question?
Yeah.
Basically,
The particle arrives in some determined position, and it's said not to have arrived in some other position because there can be.
Over again, please.
Pardon me?
Start again, please.
We observe the particle to have arrived in a particular position.
Yes.
Another particle arrives in a different position, perhaps went through a different slip. And we say these two differ because initial conditions were different. If this is true, we should be able, from the positions they arrived, to reverse engineer the math and calculate what the initial conditions were.
Of course, that's very straightforward. I mean, if we go back here and share this, sorry. Yeah, if you have a screen at the bottom, you can figure out from what its position is and go back to what the initial conditions were. But those are all inferences, not measurements.
Sure.
But yes, you just go the track backward, and you can figure out what the initial conditions were. But that's an inference, not a measurement.
Okay. So Bob, getting back to particles and waves, I gather from what you're saying is that the waves themselves, if you set up an initial state, if you measure the position of the particle to a tight tolerance, that's going to be reflected in what the waves look like. The waves are going to consist of a superposition of many momentum states. On the other hand, if you measure the momentum of the particle, that's going to affect the wave associated with a particle. So we have the same uncertainty relation that we have in ordinary quantum mechanics.
Right. Quantum mechanics, it is not a quantum mechanical result. It is the Pontryagin duality. Anything which has a Fourier transform between any two objects cannot be measured simultaneously. That's just a
Oh yeah, I understand that, but I just wanted to make sure that that is what is behind the waves in Bohmian mechanics.
oh
That
yeah.
the particle that's associated with the waves, you have the same issue of either determining the position accurately or determining the momentum accurately.
Absolutely. That's the reason that
Yeah.
you need to use weak measurements in order to be able to find the positions, because you have to repeatedly measure only a small portion of the momentum and a small portion of the position, very imprecise values, so that there is no interaction between the two, and you do it over and over and over again, and eventually, from doing a few trillion duplications, the 1 over square root of n takes you down to a very precise result. But that's a statistical average, not an individual particle measurement. However, the results look very similar to the results. And if you do the hydrodynamic version, you can track the particles, because light is very doesn't impact the momentum of the oil drop very much, the way it does in an electron.
Any other questions?
I have a question. I'm just trying to get it together here. Can you hear me?
Yeah, but get the mic over, please.
I guess we're talking about the Bohmian version, in which it appears that a particle and a wave are two separate things. And the particle rides on the wave, in effect, like a bird riding on an air wave. That's how you can kind of view it. However, we've talked before here about a particle and a wave being the same thing. Okay, it is either a particle or a wave,
They're
and
not the same thing.
viewed in a different way.
Now, the wave function is used for creating the quantum potential, and it is in the mathematics. It is exactly the same as a regular potential, but it's much more complicated, and all of the movement is due through the quantum potential, which is, let me see if I can get it back up here. All right. Okay. So the wave function is the ordinary Schrodinger equation. You write it in a different way. That's the decomposition into the real times the phase. The continuity is for the probabilities to work, and the Hamilton-Jacobi is the one that shows how the phase works as a function of the phase. V is the normal potential, and the Laplacian squared of the real part divided by 2 times the mass of the real part. It is that which creates a potential which does all of the interactions that occur in space when you are doing the so the position, the particle position is simply the gradient of the phase, and of course you need the initial conditions. And when you do that, then all of this happens because of the quantum potential.
I think what you said captures the spirit of Violet wave theory, bird riding on the.
Yeah, that's how I view it.
So the two separate things, there's the wave that guides the particle and the particles themselves. In ordinary quantum mechanics, there's not that split between the particle and waves. There's just the waves, which can be localized and look like particles, or spread out and go through 2 slits.
Right. It is the quantum potential that creates all of this movement around and creating the interference effects.
Well, when you talk about the gradient of the phase, are you talking about the first derivative?
I'm sorry, Steve. Could you repeat it for me?
I was answering for ignoring the phone.
The gradient of the phase, is he talking about the first derivative?
The question is about the gradient of the phase. Are you talking about the first derivative?
I'm talking about the spatial, the partial x, partial y, partial z of the if you have the solution of the
Essentially, yes.
Schrodinger equation, you have a real part and you have a phase part. The way in which the movement of the particle is that it is the gradient of the phase, but you can find how that phase evolves in terms of the quantum potential shown at the bottom, h bar squared over 2m grad squared of the real part divided by the real part. So there is an interaction. The particle follows the gradient of the phase, but the phase is itself a function of the gradient of the phase, the position, which is shown in the first part, minus the potential, plus the quantum potential in there. So they're interacting with each other.
Bob, maybe you've already answered this, but I have a question. In regular quantum mechanics, when you solve Schrodinger's equation, the wave function changes as a function of time. But if at some point you stop and reverse time and run it backwards, you get exactly the same result going backwards in time, which means that if you were to calculate the location of the particle at a point in time as it's evolving forward, and then you get to the same point in time as it's evolving backwards, you'd get the same position for the particle. You get the same measurement. Is that true?
Right. That's what I said here, if you had a screen up here, once you know which one of these particles it occurs at, you can work the trajectory backwards. Unfortunately, we don't know how to run equations backwards in time, so you can only infer the initial conditions.
But let me continue with my question. If you, before you run the time backwards, you make a measurement, then it's all over in regular quantum mechanics. You can't retrace the particle backwards in time.
Yeah, but that's not true in Bohmian. In Bohmian, you put a screen here. Anytime you know where the particle occurred, you can follow the trajectory backwards and figure out what the initial conditions were. But that's an inference, not a measurement.
Bob, I have this inference causes a paradox for me. If I know a Bohm applies to electrons and not photons, and astronomers observe photons, but suppose I'm an astronomer observing a star with, say, a 5-inch telescope, which has a rolling refraction disk of a second of arc. But I want to determine the position of the star to 1,000th of a second of arc. Well, then you mentioned earlier that you could look at large numbers arriving, and supposedly you're talking about electrons and not photons. I could observe a large number of electrons and infer where the star was located very accurately. Now, my question is, why can't I just observe one electron in the Bohm formulation and determine exactly where the star is located, inferentially, by back engineering the path of the particle?
I'm sorry, I didn't quite understand what you said. Steve, could you repeat it?
I don't have that good a memory, I'm afraid.
Well, let's try this again.
We need a longer cord.
Can you repeat?
Let me try and make it briefer. Suppose I cannot determine the position of the star by observing one photon, say with a 5-inch telescope. But it seems to me that Bohm says, yes, you can. If you tell me precisely where the photon arrived on the screen, I'll tell you precisely where the star is. That's inferential. I can infer where the star is. That's the paradox that's bothering.
Why is it a paradox?
Because what you're saying is I need only observe one photon and I can determine the exact position of the star if I know where the photon arrived on the screen. But I've been told my whole life by my professors that the position of the photon on the screen is probabilistically determined by the uncertainty principle. And you're going to have to observe a whole lot of them to map what the wave function looks like to find out where the star is. I can't determine the position of the star from one photon.
Well, you can't measure it going forward, but you can infer it going backwards.
Infer is the word. You got to understand, I think, what he means by infer. It means to follow that trajectory which you have already. You know that trajectory. So if you look at that point, you go back and see where it came from. He's not saying you can compute where it came from, knowing that.
But that's the paradox. And I don't care whether it's an inference or a measurement. I want to know exactly where the star is, and I'm being told I can do this with one photon.
Yeah.
You should do the computation. You have that whole trajectory, the line he drew on the screen.
I didn't understand what you said.
He's showing you a line on the screen.
Yes.
And he's saying if you pick the end point, you can follow that line back because you already.
That's right. That's the paradox.
You can't compute it.
If I follow it back, it goes back to the star. Now I know where the star is.
Yeah, that's fine. Don't you believe when you take a look in a telescope that you're looking at the position of the star?
Only by looking at a very large number of photons and not a single photon. I cannot tell the star is by looking at one photon.
Why?
How?
Well, you can't tell modulo the resolution of the telescope. Depends on the aperture.
That's true. I'd have to have a telescope with infinite aperture. But I'm being told here that I don't have to know. I can use a 3-inch telescope. In fact, astronomers use 3-inch telescopes to observe star positions to 1,000th of a second of arc, but they only observe a very large number of photons that produce a wave, the wave function, and then they look at the center of that. But if they have only one photon, they can't do that. So there seems to be a paradox here in this Bohmian formulation to me.
Well, it seems to be certainly something that is enabling, which ordinary quantum mechanics says is
It's impossible.
impossible.
Yeah.
I would think a photon going through the atmosphere could be slightly shifted by wind currents or density gradients in the atmosphere. So
Well, that's true, but
you would need many photons to really
You
know.
would have to do this in
thinking about the atmosphere, it
a
doesn't,
satellite above the atmosphere and all of those things in order to eliminate those kinds of things. But yeah, in principle, there's nothing wrong with working the position of the photon going backward to its beginning. Once you know where it was measured. And assuming you know the complete wave function of the universe. That's the other thing that is difficult to be able to figure out what the trajectory was, because normally in almost all the experiments that are done, you do very isolated small quantum systems, and you're not dealing with the wave function of the universe. You're looking at a closed system wave function. Now, in order to be able to do what you're asking to do, you would not only need to know the position, you would need to know the wave function of the universe, which is a difficult problem.
So what you're saying is if the only part of my problem with the telescope and the star and nothing else, that I cannot use the Bohmian method of determining where the star is.
Well, if you knew the wave function of the universe, you could do it. But
we've got these pilot waves sloshing around.
But there's this term that
And you've got to know where every other particle is.
You've got the Hamilton equation, that quantum mechanical term. You're saying the whole universe has to be put into that.
yeah, well, that's always a problem with quantum mechanics.
So
But that's why we deal with decoherence, because of the fact that we're dealing with systems that are not, we can't write the whole wave function of the universe.
yeah, thanks, Bob. That was a very stimulating talk. And
Okay.
next we will learn about transistors. So Ernest,
Bob, can you
Yeah.
send